Okay, in this unit we're going to introduce the concept of the atom, and then we're going to talk about the properties of atoms which cause them to bond to other atoms to form either molecules or ionic compounds, as we'll see. But first we have to talk about the atom, the building block of matter. So we'll first start talking about some of the first experiments that led to some fundamental laws of matter that led to the first theory of the atom. And of course we're going to start with the first law of conservation of mass, one we previously discussed. Remember that this said that matter, of course, cannot be created nor destroyed. This can be visualized if we think about a chemical reaction. So if we react sodium, which is a metal, solid at room temperature, with chlorine, which is a gas at room temperature, we will produce sodium chloride. Now the important part of looking at the specific reaction here is if we were to weigh the mass of sodium and say we got 7.7 grams of sodium to start with, and reacted that with 11.9 grams of chlorine, the total mass being 19.6 grams, the mass of our products has to equal 19.6 grams. So we can say that the mass of the reactants will always equal the mass of the products, so that the law of conservation of mass is conserved. Another fundamental law that was used as a building block towards the theory of the atom was the law of definite proportions. Okay, so what this basically says that all samples of a given compound, regardless of where they come from, have the same proportions of their constituent elements. Okay, we could use that sodium chloride as an example, or we could also think about water, which we know is H2O. If we decompose 18 grams of water, we'll see that that will decompose into 16 grams of oxygen and 2.0 grams of hydrogen. Okay, if we look at that as a ratio and say put 16 over 2, we'll see that that comes out to 8.0, or an 8-to-1 ratio by mass. Okay, and that will be true, again, regardless of where we get the sample. If we go to a river, a lake, the ocean, and purified the water, got rid of the salt in terms of if that was a ocean, and we just had water, the ratio of oxygen to hydrogen by mass would always come out to 8-to-1, regardless of where we got that sample. Okay, and so what we can use that ratio, or that ratio by mass, as a conversion factor to figure out constituent components of a sample, regardless of where we find them. And we can utilize that to compare two different samples. So here's an example of utilizing the law of definite proportions. So if we have a sample of magnesium fluoride and we decompose it, we'll find that we'll have 1.65 kilograms of magnesium and 2.57 kilograms of fluorine. Now we can work out the ratio of what that would be, but we could also just use those raw numbers as our ratio as well. If we grab a second sample of magnesium fluoride. Doesn't matter where we get it from, because we know it's going to have the same proportions of our first sample. If our second sample produced 1.32 kilograms of magnesium, we can figure out how much fluorine was contained in our second sample. Okay, and so by starting off with 1.32 kilograms of magnesium, symbol Mg, we know we want to go to our final answer, mass of fluorine. This time we're going to want it in grams, so we can write grams of fluorine. Okay, so all we're going to do is use this ratio, 1.65 to 2.57 kilograms, as our conversion factor, because we can rely on the law of definite proportions to tell us that regardless of what sample we have, that is going to hold true. Okay, so just like we've done before, we're going to set up a conversion factor so that our units of kilograms of magnesium cancels out. So we're going to put 2.57 kilograms of fluorine on top of 1.65 kilograms of magnesium. Kilograms of magnesium cancel out, and we wanted our final answer in grams, so we're going to have to convert kilograms to grams, and I know that there's 1,000 grams in 1 kilogram. Our kilograms cancel out, so now we're left with grams of fluorine. And if we throw that in our calculator, we'll get something like 2,060 grams of fluorine. And of course, we have 3 sig figs here, 3 sig figs in both of our values in our conversion factor, so we're going to have to limit this to 3 sig figs. And so to remove any ambiguity, we can put this in scientific notation. 1, 2, 3, 2.06 times 10 to the third grams of fluorine is our final answer. Okay, so in addition to the law of conservation of mass, which we know mass of the reactants in a chemical reaction is going to equal the mass of our products, so we can't lose any matter. Law of definite proportions, one more law gave us a pretty good understanding of the atom, and that was the law of multiple proportions. Now this one's a little bit more, how we should say, technical, but we can break it down by looking at a specific example of molecules that have both carbon, the black sphere, and oxygen, the red sphere in this case. Okay, so we know that there exists, carbon monoxide molecules with 1 carbon atom and 1 oxygen atom, and as well as carbon dioxide, 1 carbon atom and 2 oxygen atoms. So when you see that you have 2 elements that can bond in 2 different fashions, you can develop the law of multiple proportions. Okay, so what you're going to want to do is figure out the mass of each element for each of the 2 molecules. Okay, and in carbon monoxide you can see that there's 1.33 grams for every 1 gram of carbon. Okay, in carbon dioxide there are 2.67 grams of oxygen for every 1 gram of carbon. Okay, because we know in retrospect that carbon dioxide has 2 oxygen atoms, or twice as many oxygen atoms per carbon atom in carbon dioxide, the ratio, mass ratio, should be twice as much. So what we're going to do is we are going to place the mass of oxygen that combines with 1 gram of our carbon over the mass of the oxygen that combines with 1 gram of carbon and carbon monoxide, and you get a ratio of 2.67 to 1.33, or a whole number ratio of 2. Okay, and that is the big fact here, that these multiple proportions, if you're comparing 2 different molecules that have the same 2 elements comprising them, the ratio of those mass ratios will always equal a whole number, an integer. Okay, and that's what we want to take away here. Now, building on the law of multiple proportions, law of definite proportions and the law of conservation of mass, a scientist by the name of John Dalton proposed the first atomic theory, and again the theory was based on experimental evidence from these previous laws that we just discussed. Okay, the basic tenets of the first atomic theory are shown here. That of course, if we have an atom, it is indestructible, and each element is composed of those indestructible particles called the atoms. Okay, as we'll see, they're sort of not quite indestructible. They do have components of them, but each element is composed of atoms. Okay, all atoms, his second tenet was all atoms of a given element have the same mass and other properties that distinguish them from other atoms. Okay, he was almost right in this second tenet. They do have the same properties that distinguish them from the elements, but as we'll see when we discuss isotopes, the same element can have atoms with slightly different mass. Now, at the time Dalton was doing these experiments and others, they were working with sort of macroscopic quantities, lots of atoms together, so the average of those isotopes or the mass of those isotopes averaged out, which give you sort of the atomic mass of elements, and so they weren't able to distinguish isotopes quite yet. Okay, from the law of multiple proportions, we get the third tenet that atoms combine in simple whole number ratios to form molecules and compounds, and this is what really gave them a lot of their basis for the atomic theory, that you can't have half of an oxygen atom or a third of a carbon atom. They combine in simple whole number ratios because they come in whole atoms. Okay, the law of conservation of mass and law of definite proportions led to the fourth tenet, which essentially says that when you're doing a chemical reaction, atoms don't change. Okay, atoms of one element are going to stay exactly the same element that they are. They can rearrange to form new molecules or compounds, but a carbon atom as a reactant is going to stay a carbon atom as a product. It can combine with oxygen or combine with hydrogen, but it is going to be carbon. Okay, this led to the downfall of a sort of historical experiments in chemistry known as alchemy, where there was a lot of research, even by the likes of Isaac Newton, who proposed that you could turn base metals or cheap metals into more expensive metals like gold and silver. Okay, of course that would have been very profitable, but of course in chemical reactions we now know that that is not true, or not able to be done. Okay, as I said, the first tenet, that the atoms are composed of indestructible particles called atoms, was sort of slightly wrong, in that atoms do contain what we collectively call subatomic particles, which you probably already know of them. One of them being the electron, which was first discovered by scientist J.J. Thomson. Okay, what he did was he created cathode ray tubes, which you can see here. And what is in a cathode ray tube is essentially two electrodes, a cathode, conducting material, metal here, and then another conducting material, could be the same metal, over here, which we call an anode. They're connected to a high voltage power supply. And what's that going to do is going to charge these electrodes. Now, because this glass tube was partially evacuated, meaning most of the air was sucked out, when you charge these two electrodes, eventually if that electric potential becomes too great, what you see is essentially a spark arcing from one electrode to the other. Not too far removed from, seeing lightning strike during a storm. Okay, he initially called these rays cathode rays, but we now know that what was forming these cathode rays was electrons. Electrons were traveling from one electrode to the other